Hello, Mr. Collier here. Today we're going to talk about episode 6 of kinematics. We're going to be talking about gravity. So far in our discussion of kinematics, we've been talking about one-dimensional motion in the x direction, right? And really all that's different about this section of the chapter is we're going to be doing the same analysis, but everything is going to be in the y direction. So we're still going to be looking in one dimension. And if you can guess what our next chapter is going to be, it's putting it all together. So looking back, a lot of people think of Isaac Newton as the discoverer of gravity, but in reality, he was not the first person to start thinking about falling objects and gravity. He just was the first to really quantify it. Our first philosopher to really talk about gravity was Aristotle, who suggested that heavier objects will fall faster. For example, a hammer falling faster than a feather. Now, it took some time, but eventually Galileo decided to put this to the test. He was a major proponent of scientific thought, coming up with an idea, experimenting on it, and coming up with a conclusion. And so he came up with a lot of ideas about gravity, and he thought that Aristotle was wrong. He thought that how fast something fell depended on shape, the medium, and the surface area, and so to test this out, he went to the Leaning Tower of Pisa, dropped cannonballs. It was a nice tall height, so it would have a lot of time to fall. And so what Galileo found was that objects fall at a distance that is proportional to how long they've been falling squared. So, in other words, things aren't falling the same distance every second. They're falling proportionally, and they fall further the longer they've been falling. And the reason for that, right, that time squared, is because as they're falling, they're accelerating, and it's a constant acceleration. That acceleration that objects experience when they fall is due to something that we call gravity. Acceleration due to gravity is going to show up in your equations as either a little g or a for acceleration with a little g. And this is a vector quantity, and the nice thing about this is it's always 9.8 meters per second squared, or 32 feet per second squared if we're doing English. So our accelerations in this little piece of the unit are always known values. We know that it's 9.8. The direction for gravity and for the acceleration due to gravity is always down, so be careful with your frame of references. Typically down is negative, right? So our acceleration due to gravity is always negative 9.8 meters per second squared. It's very uncommon to set it up where gravity is positive, but if you did, you'd have to flip everything else around as well. Now, that 9.8 is actually an average for Earth. If you look at all places on Earth, it actually varies a little tiny bit based on how high you are above or below sea level. So in New York City, it's actually a little bit higher than 9.8, and in Denver, Colorado, where it's a very tall, high altitude city, it's actually a little bit lower than 9.8. So gravity does actually depend on your distance away from the center of the Earth. So the higher up you get, the weaker gravity gets. And gravity depends on the size of the object. So our Earth is the size of our Earth, and it has its gravity. But on the Moon, it actually has less gravity because it's a smaller body, and gravity is proportional to the mass of the object. So on one of the Apollo missions, an astronaut, David Scott, actually dropped both a hammer and a feather at the same time, and he found that they did, in fact, hit the ground at the same time. This is an artist's recreation of that, but there are videos of this as well. And the idea is that that 9.8 meters per second on Earth is constant for all objects. Now, air resistance is something that is going to affect how an object falls, and so we're going to, you'll see, ignore air resistance quite a bit in this chapter. A few terms to get familiar with. Free fall means that something is moving freely under the influence of gravity. So while its initial velocity might vary, it is always traveling at an acceleration of negative 9.8 meters per second squared. That's what free fall means. It means its acceleration is gravity. Terminal velocity means an object will maintain a constant velocity once the downward force of gravity is balanced with the upward force of air resistance, and it no longer accelerates. So terminal velocity is another way of saying the acceleration has reached zero. Terminal velocity is going to depend on a lot of things. For example, what the medium that it's falling through is, what the surface of the material is, what the surface area of it. So it's going to be different for different things. For example, something like a penny might reach a terminal velocity that's much lower than a human jumping out of an airplane. So typically those terminal velocities are going to be given to you. It's not anything you need to memorize. So we're going to do some examples now of kinematic equations, but in the vertical direction. And the nice thing here that makes it in some regards a little bit easier is that we can use acceleration is always negative 9.8 when objects are falling. So in some regards, stuff gets a lot easier. We're still going to use the guess method, but something does change a little bit. Let's take a look. So we've got the horizontal axis that you're already used to. We've been using delta x to talk about an object's displacement. Well, now we're in the vertical direction and everything's in the y direction. So you'll see that we use delta y. Our initial velocity, we had been talking about just velocity, but really we were talking about velocity in the x, and now we're going to talk about velocity in the y. Now in this section, that's not super important that you distinguish them, but later when we're talking about two-dimensional objects, like something flying through the air like this, then yeah, you're going to need to do both. Time, of course, is the same in both, and that's good. And acceleration, we used to have to figure it out, but now, hey, guess what? Acceleration is always g, negative 9.8. Yay! And so here are those kinematic equations. It's exactly the same as what we did before. I've just swapped out all of my delta x's for delta y's, and my initial and final velocities now have little y's in them as well, and so do my accelerations. So just like everything we've done so far in our kinematics, we're going to analyze these problems using the guess method. So if I look at Freefall, which is a ride at Six Flags Great Adventure, you free fall for 2 seconds. What's the displacement that you fall during that time, and what's the top speed? So it might seem like you don't have a lot of information, but you actually do. When you're at the top of the ride, you're not moving, so your initial velocity is 0. Your final velocity is unknown, and that's what we want to find out in Part B. But we do know the acceleration. It's free falling, that's the name of the ride, and so the acceleration due to gravity is negative 9.8, and we know that it falls for 2 seconds. So our delta x becomes our delta y, and that is how far does it fall. So first we're going to solve for the delta y. We know the initial velocity is 0 and it falls for 2 seconds, and gravity is negative 9.8. This allows us to solve and simplify, and we can figure out the delta y. Now notice, because our acceleration is negative, we get a negative displacement, and that makes sense. This is an object that has fallen downward, so its displacement is negative. For part B, we're going to pick an equation that lets us solve for the final velocity, and we know its initial velocity and gravity and time. So we're going to, again, sub in our numbers and solve. So now we can figure out, as objects fall, we can figure out how far they will fall, how fast they'll be going based on how long they've been falling, and it's very similar to the kinematics, just with a little twist. So here's another sample problem. We're going to throw a tennis ball into the air directly upward with a velocity of 22.5 meters per second. We want to know how high it will go and how long will it be in the air. So we know its initial velocity and gravity is pulling it down. We want to figure out how long it'll be in the air and what its maximum height is. So the ball's going to go up and it's going to come back down. It'll stop briefly at its apex, but the entire time gravity is pulling it back down. So really, what we know is that at the apex, and this is a tricky thing that we need to remember, if something goes up in the air and comes back down, at the apex, which we would consider kind of halfway through its ride, the velocity is briefly 0 as it turns around. That'll come up in a lot of problems here. So now we can solve for how high it goes, what its maximum displacement is, and we're going to figure that out using this equation, solve for delta y, and we can figure out the maximum height that the object will achieve. So how high it goes, as you can see, depends heavily on what its initial speed was. From that, we can figure out how long it's going to be in the air. The trip up will allow us to calculate the time, and then we can actually just double that for the total time in the air. So for the trip up, we've got our variables. We're going to sub in to figure out how long it's in the air. And now since that time that we just solved for is only the trip up, we're going to double it and get the total time that it's in the air. There's actually another way you can settle this as well. We can say that if its initial velocity is 22.5 meters per second, trips like this, when you throw something up in the air and it come back down, they're very symmetrical, so its final velocity will be negative 22.5 meters per second. It's going to have the same speed on its way down that it had on the way up when it gets to the same spot. So solving it that way, the delta y would be 0, and we can solve for the total amount of time. This will give us our answer directly. So two different ways to do it. You can treat it as just getting to its apex, figuring out the time and doubling it, or you can realize that the final velocity is going to be the opposite of the initial velocity and solve it using that method. Hopefully that gives you a better understanding of gravity and free fall and how it fits into the kinematic equations. Good luck.